Welcome to the video lecture series for Texas A&M University Course Math 152. Today we will take a look at section 10.5 Power Series. You can find the accompanying handouts at bit.ly/Raelene Math 152. Let's begin. As a warm-up, let's write the equation of a circle with a domain of x contained from -2 to 8 and a range y contained from -11 to -1. Well, if we were to just sketch this, we could easily see the circle going from -2 to 8 and therefore having a diameter of 10, which is 8 minus -2, and we have a diameter vertically from -11 to -1, which is also a change in y of 10. And so we have the diameter is 10, which is a change in x, which happens to be the change in y from the domain and the range, which is equal to 10, and therefore the radius is equal to 5. We can also come up with the midpoint x coordinates from the endpoints, which is going to be located at the average, -2 plus 8 divided by 2, which is going to give us a center at 6/2, which is 3. And we also see that we have the average y coordinate, -11 plus -1 is -12, divided by 2 is -6. And so we could put our vertex points here at a height of -6. We have -2, -6. We have 8, -6. And in the vertical line of 3, we have a point below at 3, -11. And at the top point, we have 3, -1. And so we have the center, and we have the radius. Therefore, the equation of the circle is given by x minus 3 all squared plus y plus 6 all squared equal to 5 squared. In number 2, solve for x. Include a one-dimensional sketch in your solution. There are many approaches that we've seen in the past for solving inequalities. My least favorite is the one that says x minus 3 equals -1 or x minus 3 is equal to +1. The reason I don't like that is because students don't seem to know why there's an or, and it also mistakenly or cements a misconception that the plus or minus belongs to the 1, when in fact we know that the absolute value definition says that to remove the absolute values, if the stuff inside is negative, you change the sign of the inside. And if the stuff inside is positive, then you do nothing or don't change the sign of the inside. That is also true if the stuff x minus 3 inside is equal to 0. And so the plus or minus really belongs to the x minus 3 and not to the 1. So I would prefer to see the negative on this side and the positive on this side than on the opposite side, because when we get to an inequality, we will already have the plus or minus on the wrong side. But another reason I don't like this is because it does not allow us to consider extraneous solutions, and it does not allow us to work very well with the inequalities, for which we should be thinking graphically. I don't, however, think a two-dimensional approach is necessary when it comes to this particular inequality or equation, because we can think of the definition of absolute value as distance. And so if we see the absolute value of x minus 3, we should be reading that as the distance. Absolute value means distance. The subtraction means between two things. So the distance between x and 3 is one space. If we had had absolute value of x plus 4, we would read that as the distance between x and -4. And so from this perspective, reading absolute value as distance, I want to see that this means the distance between x and 3 is 1. In other words, x is 1 unit away from 3. And we can kind of see 3 as a center, much like we saw 3 as a center for the equation of the circle. So from that perspective, we know that on the x number line, 3 is the center, and x is going to be 1 unit away, taking x to either 2 or 4. And so the solution for the first equation is x equals 2 or 4. Then continuing on with this in part B, we have that the distance between x and 3 is less than 1 space. And so if we use the one-dimensional number line system again, a one-dimensional graphical approach, we have that x is going to be less than 1 space away from 3. So if we go exactly 1 space away from 3, we would end at 2 or 4 again. But x is not allowed to be exactly 1 space away from 3, so x is not allowed to be 2 or 4. So are the x values that we want between these boundary values or beyond these boundary values? And since we want x to be less than 1 space away from 3, we want x to be between. So in part B, the solution is 2 less than x less than 4. And I'm just going to put that all side by side. And so the solution, and this is x for the x number line. And then in part C, we have the same number line, the same boundary values, but the inequality is interpreted somehow differently. We want x to be more than 1 space away from 3. So to be exactly 1 space away would take us to 2 or 4, but we want x values that are more than 1 space away. And so we have x is less than 2 or x is greater than 4. Okay, in number 3, to what absolute value inequality is the interval -3 less than x less than 8 a solution? Well, let's sketch the solution set. And we realize that we are going to be working backwards from one of the 3 cases in number 2, and we have case B. So we need to find the center of the inequality and the distance or radius. We are going to be seeing this 1 as the radius of a circle, not unlike the radius of a circle that we saw here if we had been considering an x-axis and an interval in between. So we could be looking purely along an x-axis and looking at an interval distance of so much, the radius, or we could blast this radius and the coordinates not just along the x-axis but along a vertical axis and get a 2-dimensional circle picture. These are the one-dimensional projections of the 2-dimensional picture in part A. So here we want to consider, yes, maybe we do have a circle. So what we need for the circle is the center, and this center is going to be the midpoint of -3 and 8, which is going to be 8 minus 3, which is 5, divided by 2. And then we need to come up with the radius, and that radius value is 8 minus 5 halves, or 5 halves minus -3, or half of the diameter, 8 minus -3. So we get that the radius is 11 over 2. And so we can see that we have the inequality that we would have had to solve. The absolute value inequality is x minus the center, which is 5 over 2, which is less than, because we are between the boundary points, 11 over 2. And if we double both sides of this inequality statement, we preserve the inequality, and we end up with 2 times the absolute value of x minus 5 halves is less than 11. And then 2 is the same as the absolute value of 2, and then we can combine these into one absolute value statement by multiplying the 2 through. And so we end up with a statement of the absolute value of 2x minus 5 is less than 11, has the solution of -3 less than 8 less than x. In number 4, we want to solve a similar inequality, the absolute value of x minus a less than r for x, and express the set on a number line. So our number line has a center of a, just like a horizontal translation of a, spaces to the right as long as a is positive, and we are talking about a one-dimensional distance of r away. So if we go r to the right, we take a and we add r. And that's assuming, of course, that r has to be a positive number or equal to 0. It wouldn't make sense for r to be negative and to be a distance or a radius. And then if we go r to the left, we are ending up at a minus r for going left r spaces. So x is any value, not exactly r spaces away, but less than r spaces away from the center of a. And so our solution is x contained in the set from a minus r, comma, a plus r. Now it should be pointed out here that whether the endpoints are included or excluded, that the radius is still r. The radius doesn't mind if the endpoint is not there. The distance between the two endpoints is irrelevant of whether the endpoints are included in the set or not. In number 5, we are given that -1 is less than r, which is less than 1, and r is equal to negative x squared, so solve for x. So we can make the substitution for r equal to negative x squared. And if we do that, we have to be really, really careful in working with inequalities. I would prefer to work graphically. So I'm going to see a horizontal line of y equals -1, a horizontal line of y equals 1, and the curve y equals negative x squared. And we want the blue curve to be bounded between the red and the green curves. So y equals negative x squared is a concave down parabola. Y equal to 1 is a horizontal line above the x-axis. And y equals -1 is a horizontal line below the x-axis. And we can see that y equal to 1 actually has nothing to do with the boundary of the blue curve, because the blue curve is actually bounded above already by the x-axis. So the highest the blue curve ever gets is a height of 0 anyway. So we can actually state that this is equivalent to 0 being less than or, -1 is still valid. It's the green one that's not valid. -1 is less than negative x squared, which is less than or equal to 0, because the blue curve never gets as high up as the green curve. And so look for the x values for the points of intersection. We have the x coordinates are located at -1, 0, and 1. And so what are the x values that make the blue curve bounded between the red curve, y equals -1, and the black curve, y equals 0, or the x-axis? Well, we know that the boundary that we're looking for, or the portion of the curve that we're looking for, doesn't include these endpoints, but it includes everything in between. And so the x values we are looking for are from -1 exclusive to 1 exclusive. So trying to go from the first line to the second line, or the second to the third line algebraically, does not work. So please make sure that you are solving inequalities graphically. In number 6, what are the names of each quantity in the equation b to the x equals p? B stands for base, x for exponent, and p, the result of a base raised to an exponent, stands for power. The reason this question is here is to remind us not to call the little number up as an exponent on the base. Do not refer to it as a power. Number 7 asks, what name is given to functions of the form y equals a times x to the n, where a and n are constant? That means that the variable is x, and since the variable is located in the base, we have a power function. Now, power functions can have any exponent n, positive, negative, 0, fractional, etc. However, even irrational numbers like the square root of 2. But when we are building polynomials, we know that the exponents for n in polynomials are only positive integers or 0. So 0, 1, 2, 3, 4, etc. Those would be the terms that show up in polynomials. Number 8, state the exponent and the power for each expression. So in part A, the exponent is 3, and the power is the base raised to the exponent x cubed. In part B, the exponent is x, and the power is the base raised to the exponent, namely 3 to the x. Again, just a reminder not to confuse the exponent with the power. And so what are the names of each function? Y equals x cubed has a variable in the base, and therefore this is called a power function. Meanwhile, y equals 3 to the x shows the variable in the exponent. And when we have the variable in the exponent, we refer to such functions as exponential functions. So you should be noticing a trend as we are moving into to chapter 10.5. We are starting to talk about functions again, which have the continuous variable, x contained in the reals, as opposed to sequences and series, which have the discrete variable n contained in the integers. And what we are going to do in the remainder of chapter 10 is to connect the discrete sequences and series to the continuous functions, where x is contained in the reals. In number 10, a finite sum of power functions whose exponents are whole numbers and whose coefficients are real numbers is referred to as, well, if we have power functions of the form a times x to the n, but n is a whole number, and the coefficients, maybe these are coefficients an, a1, a2, a3, etc., then when we have a sum of these, a finite number, this is a polynomial. So for example, we might have y equals 2x to the 7 minus x to the 6 plus 3x to the 5 minus 2x squared plus 8. That would be a polynomial. Number 11 asks which kind of series is each below and determine whether it converges or diverges. And if it converges, and you can, determine its sum. Well, we notice that in the first series, the variable of the series is n. And n shows up in the exponent, and therefore we have a geometric series. Furthermore, the value for r is equal to 1/2, which in absolute values is less than 1. And let me just put the absolute value of r equals, well, let me write it like this. R is the same as the absolute value of r, which is equal to 1/2, which is less than 1. So therefore we have a convergent series, or a convergent geometric series, and the sum is s equals a over 1 minus r, and we see that the r value is 1/2, and the a value we should be very careful with. If we expand the series, n equals 1 to infinity of 3 times 1/2 to the n minus 1, then when n is equal to 1, we have 1/2 to the 0 times 3 is 3 times 1, which is 3. Plus, now we don't need to work so hard because we know every subsequent term will be multiplied by, each term will multiply by 1/2 to get the next term. So we get plus 3 over 2, plus 3 over 4, plus 3 over 8, etc. And so we can confirm that indeed this 3 happens to be the same as the a value. And so the a value is 3, and we get 3 divided by 1/2, which is 3 times 2, which is 6. So I'll leave you to do B and C. However, I do want to point out, if we expand part B, that the sum from n equals 1 to infinity of 3 times 1/2 to the n is going to give 3 times 1/2 to the 1, which is 3 over 2, plus 3 times 1/2 squared, which is 3 over 4, plus dot dot dot. And whether we have a convergent or divergent series, or we know that we have geometric, we also know that a is not 3 because the first term in the expansion is 3 over 2. So do pay attention to that when you're finding the values for a and r from a geometric series. So finish parts B and C, and you can check your answers in the completed lecture notes. Number 12 asks, do this geometric sequence and the geometric series converge for r equal to 1? Well, let's just remind ourselves what the meaning of a what the condition is for convergence of a geometric, for any sequence. A sequence an converges if the limit as n approaches infinity of an exists. Meanwhile, a series an, which is equal to the limit as n approaches infinity of Sn, must exist, which means be finite. And I'm just going to put n equals 1 to infinity here. Must exist or be finite for the infinite series to converge. Note that if the limit as n approaches infinity of an does not equal 0, then this series, or the limit as n approaches infinity of Sn, will not be finite. Okay, so you might want to think about that and ask a few questions. This goes back to the nth term test for divergence. So the nth term test for divergence is only a test to say that we can be sure if that a series diverges if the nth term of the sequence does not approach 0 as n approaches infinity. However, if the nth term does go to 0, then we cannot conclude whether or not the series converges or diverges, and we would have to use another test. Okay, so this is a reminder of what it means for a sequence or for a series to converge. And so now let's take a look at the geometric sequence. With r equal to 1, we end up with a times 1 to the n minus 1, which is the sequence of a, and the limit as n approaches infinity of a is equal to a, which exists. Therefore, the sequence converges. The geometric sequence converges. Meanwhile, the geometric series with r equal to 1 is going to be a times 1 to the n minus 1, which is a series of a from n equals 1 to infinity, which, if we expand it, is equal to a plus a plus a plus a plus dot dot dot. Well, there's two ways that we can understand this. Let's think of the series as an accumulation. And for our accumulation, if a is positive, then we have an along here and n along here. And so we're getting, let's say the a value is this height. So we have a. And of course, each of these can be multiplied by 1. So we can consider that these are rectangles of height a and width 1. And there are an infinite number of them. So will we have a finite or an infinite amount of area for non-zero a? So we have infinitely many rectangles of area a times 1 equal to a. Therefore, infinite accumulation. And therefore the series diverges. In other words, we could say, and I think I'm going to pick all this up, copy it and cut it, and put it on the next page. And so what we can also say is that the limit as n approaches infinity of a times r to the n minus 1 will equal the limit as n approaches infinity of a when r equals 1 which is equal to the limit of a, which does not equal 0 unless the first term is 0. And therefore, by the nth term test, for divergence, the geometric series with r equal to 1 diverges. And so just to summarize once again as a warm-up, that the convergence interval, or the values of r for convergence of the geometric sequence converges for r contained from -1 to +1 inclusive, but not including -1. And the geometric series converges, let me write all this down, it converges for r contained from -1 to +1 open interval, and it converges furthermore to the sum a over 1 minus r. This is a very important result. I'm repeating it from section 10.1 and 10.2 because it is so important. In number 13, we want to write an expression for the nth term of the geometric series and determine the sum of the series if it exists. So again, we're coming up with some practice writing the nth general term. We see that we've got 1 over 1 minus 1 over 2 plus 1 over 4. So at this point, we really might want to come up with some patterning, and we can recognize that the denominator are all the powers of 2, including the first denominator, which is 2 to the exponent of 0, minus 1 over 2 cubed plus dot 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 plus the nth term, which is going to be -1 to some exponent over 2 to the exponent of, well, this is where it gets interesting. It depends on what we're using for n. We could start the series with n equal to 0 because we have an exponent of 0 and then 1 and then 2. And so then later on we're going to get to n equals n, and so this is going to be 2 to the n, and for even values of n we have a positive term, and for odd values of n we have a negative. So we start off with n here, and we see when n is 0 we would get -1 to the 0 is positive. If n is 1, -1 to the 1 is negative. And so that looks like our general term. So therefore the series will be given by the sum from n equals 0 to infinity of -1 to the n over 2 to the n. And so we see that the variable is in the exponent. We could also rewrite this as n equals 0 to infinity of -1/2 to the exponent n. And so we can see that we have an r value of -1, which is contained in the interval from -1 to +1. So we have a convergent series, and furthermore we have an a value of the very first term, which is 1. And so therefore the sum is equal to a over 1 minus r, which is going to be 1 over 1 minus -1/2, which is equal to, I'll expand that a little bit, one minus 1/2 is 3/2, and the reciprocal of that is 2/3. Okay, I'll leave you to try part B on your own, and you can check with the lecture notes at the end of the video. The next thing we're going to talk about then is, after the warm-up, what is a power series? So a definition of a power series is a series centered at x equal to a, which is an infinite sum of powers of x minus a. In other words, the infinite sum of powers of x minus a without the exponent. We have integer exponents on n and real coefficients cn. So whatever the base is, we are talking about powers of that. So if I said the powers of 2, I would have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. And therefore the powers of x minus a are x minus a to the 0, x minus a to the 1, x minus a to the 2, etc. So I really shouldn't have had the n there. And so we have integer exponents, and also these should be positive and 0, or non-negative integer exponents, and real coefficients Cn. We're using C for coefficient, and n just to say that it's for the first term, the second term, the third term, etc. In other words, we're finding that a power series is an infinite polynomial. In number 14, to clarify the power series, we're asking, what is the variable of the series? So the variable of the series is the variable of the summation, and the variable of the series is n. And if we write the 99th term in the series, we have to recognize the way that we are indexing the summation, we're starting at n equal to 0. So n equals 0 corresponds with the first term, and n equals 1 corresponds to the second term. And so if I want the 99th term, the value for n is going to be 98. And so the 99th term in the series is going to be c subscript 98, whatever that coefficient is. It might be -7, it might be 1/2, it might be the square root of 2. And we have x minus a for whatever the center is, wherever we are translating to zoom in, like for a line of tangency. And we have the exponent of 98. In number 16, let's write the series in expanded form using the first 5 terms centered at -2. Well, we still don't know the coefficients, but we're going to say that the series is given by c0 times x minus -2 to the 0, which is actually just going to be c0 times 1, which is c0. And then plus c1 times x plus 2 to the exponent 1, plus c2 times x plus 2 to the exponent 2, plus c3 times x plus 2 all cubed, plus c4 times x plus 2 to the 4. And then plus dot dot dot. We're only expanding using the first 5 terms, but it's still an infinite series. In number 17, as a reminder, what are the values of r for a convergent geometric sequence? We know that r is contained from -1 to 1, including 1, but not -1. And for the series, we have a pure open interval from -1 to 1. Number 18 asks, if the power series is geometric, then what must be true about the coefficients? Well, if this is a geometric series, then we know that we have a common ratio. And if we have a common ratio, then we are taking C0, multiplying it by a ratio, multiplying by a ratio, multiplying by a ratio, and so the coefficients C0, C1, C2, etc. must be the same. So the coefficients are constant. And let's just write C0 equals C1 equals C2 equals dot dot dot. And furthermore, the common ratio r has a value of, well, in this example 16, it's x plus 2, but in general, it is the value of x minus a. But of course, if C0 doesn't equal C1, then we did not take C0, multiply by a ratio, and get C0 times x minus a. So it's only if the coefficients are equal, then the common ratio is equal to x minus a. Number 19 says that the sum of a convergent infinite geometric power series, so if it's a geometric series that is a power series, we know that we have a certain r value and all of the coefficients are constant. Well, we're given that the sum is here, 3 over 1 minus x squared over 2. So we know that the sum is equal to a over 1 minus r, which is given as 3 over 1 minus x squared over 2. And so we can see that a must equal 3, and write this out a bit differently. A is equal to 3, and r is equal to x squared over 2. But let's be really clear, if we have a power series, then we have coefficients C0, C1, C2, C3, etc. And the reason we say C0 is because 0 has often been referred to as naught. And naught is spelled N-O-U-G-H-T or sometimes N-A-U-G-H-T, and it means nothing. So this is 0. So C naught or C0. I find it easier to say C naught. And so anyway, the A value is the constant for all of the coefficients. C naught equals C1 equals C2 equals every Cn coefficient. Okay, in part B, write the geometric series in both expanded and sigma notation. Well, now that we know A and R, and we have a geometric series, we can say that the series S is given by 3 plus 3 times the radius plus 3 times the radius squared plus 3 times the radius cubed, etc., which is going to be 3 plus 3 over 2 x squared plus 3 over 4 x to the 4 plus dot dot dot, and we can write that. We could factor the 3 out of the sigma if we wanted to. We should also recognize what's going on with our index. So we have n equals 1, 2, 3, or we could have n equals 0, 1, 2. I like using n equals 0, n equals 1, n equals 2, because then I can see the patterning with the exponents. This is really x to the 0, and we have 2 to the 0. So I'm going to write it in summation form as 3 times x squared over 2 for my radius, or my ratio rather, n equals 0 to infinity, and if this is my exponent n, the first time through n is 0 means that we have 3 times 1, which is 3. The next time through n equals 1, we have 3 times x squared over 2, all to the 1, which is correct, and so on it works. In part C, we are defining an important term called the interval of convergence, and the interval of convergence is given by capital I. It is the set of x values for which the series converges. So what is I for this series? Well, we know that a geometric series converges when r is contained from -1 to 1. But r is x squared over 2, and it has to be contained from -1 to 1. So if we write this as an inequality, we know that -1 is less than x squared over 2, which is less than 1. And this reminds us of the warm-up question, where we were solving a compound inequality for x. You can do some algebraic manipulation of the inequality, but you should confine it to multiplying by constants and adding and subtracting. So if we multiply both sides or all sides of the compound inequality by 2, then we can solve graphically. And when we solve graphically, we have, I'll use 3 colors again, y equals -2, y equals +2, and y equals positive x squared. And so looking for the x values that keep the blue curve bounded between the green and the red curves, we see that the red curve is not important, and the boundary that we are looking for is simply the yellow highlight or the yellow drawn portion. And so we've got some points of intersection between the blue curve and the green curve at -√2 or +√2. And therefore the interval of convergence is the set of x values that satisfy that inequality, namely from -√2 to +√2. Now before you get very excited and think, I simply could have taken the square root of all 3 of these sides, consider what would have happened if you had taken the square root of -2. That's not the same as negative the square root of 2. So please remember to solve inequalities graphically. In part D, we are defining the width of the interval I to be the diameter of convergence, but more importantly, we want to talk about the radius of convergence. So we can see that the diameter of convergence, D for diameter, is going to be x final minus x initial, or the right end x coordinate minus the left x end coordinate, which is going to be square root of 2 minus negative square root of 2, which is 2 square root of 2, and therefore the radius of convergence is equal to half of that, the square root of 2. In other words, it's very much like the solving absolute value inequalities and the radius and range and domain of a circle that we saw in the warm-up. In number 20, we are asked which power series below are geometric and how can we tell? Well, we know that a geometric sequence term has the variable n in the exponent. And so for the series, when n shows up only in the exponent, we have a geometric series. So geometric series implies that the variable of the summation, or variable of the series, which is n, shows up only in the exponent, meaning there is a base, which is not n, and then we have an exponent. So in the first term, we have n showing up in the factorial as well as in the exponent, so a is not a geometric series. In part C, we have x is a variable, but is not the variable of the series. It's the variable of a function that we will get, which is an infinite series, but it is not the variable of the summation. N is the variable of the summation, and we have n showing up only in the exponent. So in part C, we do have a geometric series. Part E, we have the square root of n minus 1. N is in the base, and so we do not have a geometric series. In part G, we have n plus 1 in the exponent, and we have n in the denominator exponent. We also have x in the base, but x is not the variable of the series. Therefore, G is a convergent series, a geometric series. In part B, we have the variable n in the exponent, but also in the denominator as a base, so B is not a geometric series. In part D, we have n in the exponent for the numerator, but in the denominator it is in the base for a factorial, so we do not have a geometric series. In part F, we have n in the exponent, but we also have n in the base as some kind of hybrid term, and so F is not geometric. In H, we don't have n at all, which means that we could say 5/4 is being multiplied by 1 to the exponent n, and since n shows up in the exponent, we do have a geometric series. Of course, in this case, r is equal to 1, and so we do not have a convergent geometric series, we have a divergent series. There are three possible radius of convergence values then for power series. We could either have, and we're going to be using A as the center of the series, or the horizontal translation of the series, just like we saw A was the center of the absolute value equation and inequalities that we solved in the warm-up. The first possibility is that the radius of convergence is infinity, which actually means the interval of convergence is the entire real line. So we could have the center being 0, and we could go to positive infinity on the right and negative infinity on the left. So those would be the x values which make the power series converge. But we could also be starting at -8 and then going positive infinity to the right and negative infinity to the left, and that would still be the center of convergence of -8 with a radius of convergence of infinity. So if we have the radius of convergence is infinity, that means that the geometric series, or rather the power series, is always convergent, no matter what value of x shows up in the power series. The second value for the radius of convergence is 0, which means that the power series will only converge at the center of the series, namely when x is equal to a. And the third possibility for the radius of convergence is that there is some finite positive value of r. Of course, r for radius has to be positive, which is why I've put it in parentheses. And furthermore, the interval of convergence can be found by solving the absolute value inequality that x minus a in absolute values is less than r. And of course, we've seen that this means that x is contained from a minus r on the left to a plus r on the right. We do not know what happens at the endpoints of this interval, however. Perhaps when x is equal to a minus r, and we substitute into our power series, remember the power series has a form n equals 0 to infinity, the sum of Cn times x minus a to the n. And so perhaps when x is equal to the left endpoint, we end up with a series which converges. If that's the case, then we must include the left endpoint. And perhaps when we take the right endpoint and substitute in for x, we get a series that by some test, maybe the alternating series test, or maybe the p-series test, or a comparison test, maybe in that case we end up with a divergent series, so we do not include the right endpoint. So what this is saying here, note that each x-coordinate of the endpoint of the open interval must be tested separately for convergence. This means that we substitute the left endpoint or the right endpoint into the series and test the resulting series, which, by the way, no longer involves x because you've substituted a value in for x. And the resulting series for the left endpoint or the right endpoint must be tested for convergence, using the tests that we have seen in 10.3 and 10.4. In number 21, then, to clarify what we've just read, true or false and explain. Every power series of this form converges when x equals a. Well, even if we have a radius of convergence of 0, which means that trying to draw a circle around the center point, and the center is at a, we would have a circle of radius 0. So that means we're just at a point. And when we have a radius of 0, there is still convergence at x equal to a. So, true, every power series converges at the center, and maybe for even more x values. Maybe for only the center, that's what part number 2 says. Maybe for every x coordinate, for x contained in the reals. Or in number 3, maybe for some interval, which is a pure open, half closed, or a fully closed interval. So now let's take a look at some specific examples of what the radius of convergence and the interval of convergence look like. Let's take the previous 8 power series from a to h. I've written them again here, and let's test them for convergence. If the series converges, let's furthermore state the interval of convergence, the set of x values for which the power series converges, and also make sure to check convergence at the endpoints. And furthermore, we will determine the radius of convergence. So I'll take 2 of them. I'll take the first 2, and then you can practice the rest of them on your own. So in part A, we have the series. I believe it's from n equals 0 to infinity of n factorial times x to the n. If you recall, in 10.4, we talked about the ratio test, and we said that the ratio test is the test that we will use to determine the radius of convergence and the interval of convergence. So what we're going to do is evaluate L, the limit. So let's right here use the ratio test. And we're going to evaluate L as the limit as n approaches infinity of the absolute value of an plus 1 over an. And I'll work down in a column. This gives the limit as n approaches infinity. And don't forget, I can divide by an or multiply by the reciprocal of an. So I'm going to get the absolute value of n plus 1 factorial times x to the n plus 1 divided by n factorial times x to the n. Now keeping in mind that n is greater than or equal to 1, or rather 0, and n plus 1 factorial and n factorial will always be positive, these factors or expressions do not need to stay inside the absolute value. However, x is a variable of the real persuasion, meaning it could be contained in the reals. So x could be negative, which means it needs to stay inside the absolute values. And we can simplify this, giving that limit as n approaches infinity of x to the n plus 1 is really x to the n times x, and so we can reduce x to the n top and bottom, and we're left with this absolute value of x multiplied by n plus 1 times n factorial divided by n factorial, and we can reduce the n factorial. Now the variable of the limit, like the variable of the series, is n, and therefore x, while being a variable, it is not a variable of the limit, so it is constant and can come in front. And then we take a look at this linear expression as n approaches infinity, n plus 1 approaches infinity, and we have that the limit is equal to infinity. So by the ratio test, we know that the L value is greater than 1. So because L is greater than 1. It's really greater than 1. It's infinity for all x values. Therefore, there's only one x value which would pose a problem here, and that's the x value which makes this expression 0, so that the entire expression would be indeterminate. In that case, I shouldn't say L is greater than 1 for all x contained in the reals. This is true for x not equal to the center value. And what is the center value when we have just x? It's really x minus 0. So as long as x is not 0, the limit value is going to be greater than 1. Therefore, by the ratio test, these numerator terms of n factorial are simply growing too fast for this power function of x to bring the end behavior to the horizontal asymptote of y equal to 0. And so by the ratio test, the series diverges for all x not equal to 0. So what we are asked is to state if the series converges, but we can still answer B and C, because when we have the series diverges, we still know that there is one x value for which the series will converge. So we know that the series diverges for all x not equal to 0. However, the interval of convergence is going to be x contained with one single value, and the radius of convergence is going to be 0. So this goes back to the fact that we have a radius of convergence corresponding to only the center of the series, producing a convergent series. And so then, furthermore, we will take a look at part B, which is a series starting at n of x minus 3 to the n over n. So the sum from n equals 0 to infinity of x minus 3 to the n all over n. So we will use the ratio test to work out the limit value. And the limit as n approaches infinity of the absolute value of an plus 1 times 1 over an is going to give the limit as n approaches infinity of x minus 3 to the n plus 1 all over n plus 1 multiplied by the reciprocal of an, which is going to be n over x minus 3 to the n. And from here we can simplify. The n plus 1 expands as x minus 3 to the n times x minus 3, and so we are left with x minus 3 in the numerator, and we have n over n plus 1. Again, the x minus 3 in absolute values is a constant as far as the limit is concerned, and so we can pull that factor in front of the limit, that constant, and then we can take the limit as n approaches infinity of the absolute value of n over n plus 1. But recall that absolute value of n over n plus 1 is unnecessary because n over n plus 1 is always positive for n greater than or equal to 0. So I should say positive or equal to 0 because at the first n value, this fraction is 0. So it's greater than 0 or equal to 0. So the point of all of that is to say we don't need the absolute value. And the limit as n approaches infinity, we can think back to rational functions. We have linear over linear, so we will get a constant quotient and a horizontal asymptote. This limit then is equal to 1. And so what we're finding then is that we have a variable value for L. And L is equal to the absolute value of x minus 3. And so we know that for our series to converge, L has to be less than 1. Therefore, absolute value of x minus 3 must be less than 1. And so the nicest way to solve for this, I think, is thinking verbally and coming up with a one-dimensional number line. And so we have on the x-axis that we have a center of 3, and x is at most 1 space away, which means that x could be 2, not be equal to 2 or 4, but could be anywhere in between. So it seems like we are getting an interval of convergence, a set of x values that makes the series converge from 2 to 4. However, we have to test at the endpoints to see what happens. So we're really not finished testing convergence until we continue to find the interval of convergence. So what we are going to do is test the series for convergence for x equal to 2 and for x equal to 4. So when x is equal to 2, the series turns into the series from n equals 0 to infinity. And if you recall, it was x minus 3 to the n over n. So when x is 2, 2 minus 3 is negative 1, and we end up with negative 1 to the n over n. And we should recognize this. This is the alternating harmonic series, which from before we have proven to converge by the alternating series test. Now, we should be very careful when we're talking about the alternating series test. We have to talk about conditions 1, 2, and 3. But we can also take the alternating harmonic series as a basic series. So unless we are asked to show or to prove that the alternating harmonic series converges, we can state we know it does because it is a basic one. But here I'm just reminding the alternating harmonic series converges by the alternating series test because conditions 1, 2, 3 are true, and therefore x equal to 2 is included in the interval of convergence. Then if we repeat the process testing for x equal to 4, we get the sum from n equals 0 to infinity of x minus 3, which is 4 minus 3, which is 1 to the n, divided by n, which of course is simply the sum from n equals 0 to infinity of 1 over n, which is the harmonic series, which diverges, and we've seen a number of ways and repeated it through the videos in 10.3 and 10.4, which diverges because it's a basic series. It's a p series with p equal to 1, and we also know that the nth partial sum grows unbounded as n approaches infinity. And so we do not include x equal to 4 in the interval of convergence. So we can say that we can kind of combine a and b. The series converges for the interval of convergence I, which is 2 less than or equal to x less than 4. And then in part C, the radius of convergence is nothing more than, imagining we had a circle here. What's the radius of that circle? The radius is equal to 1. And so the radius of convergence of 1 is it's independent of whether the endpoints are included or not, because the distance between the center and the edge are the same whether the edge is included or not. So we have a radius of convergence of 1. So you have 6 more series that you can practice, finding convergence using the ratio test and determining the interval of convergence including the endpoints, and therefore coming up with the radius of convergence. Keep in mind for this last example, we had a diameter of convergence of 2, and therefore the radius was half of the diameter. This concludes section 10.5, Power Series. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.